Hi everybody, Physics Ninja here. Today I've got a great problem for you. I recently got the trim on my home repainted, and this is what it looked like. We had a painter standing on a ladder leaning up against the house, and I thought this is a wonderful physics problem, an equilibrium problem dealing with forces and torques. So let's have a look at this problem. Let's draw free body diagrams and figure out what is the minimum angle that this painter can set up his ladder and safely paint the trim on my home. All right, let's have a look at the problem. I just want to consider the ladder by itself for a minute just to set up this problem. So in this case here, I've defined the angle down here that the angle of the ladder makes with respect to the ground. I'll call this theta. Now you can imagine if I make this angle smaller, what would it look like? Well, if I make the angle smaller, the ladder might look something like this. And if you've ever set up a ladder against a wall, you probably do not want to set it up like this, right? This would be kind of a theta small angle. Right? Because you know if you set it up like this, and it might hold for a little bit, but as soon as you step on it, for example, if somebody stands on it, you know there's a risk of it kind of dropping, right? It would fall and then someone might get hurt. You don't want to do that. The other thing you do know is if you set it up with a large angle, right? If you set it up kind of very close to the wall, for example, it might look something like this. You know that this would also probably hold you. However, you know if you've been on a ladder like this, it's sometimes a little scarier because it's so steep, right? But in this case here, this angle here, this angle theta here would be a large angle. So there is kind of some minimum angle. You probably can't go all the way to this picture over here, but you can probably get to some minimum angle, and that's kind of what we want to find here, is what is the minimum angle that you can go to before it starts to slip. So let's go ahead now and set up the forces and see how you solve a problem like this. Okay, so for this problem here, again, I want to find the minimum angle that the ladder can make in contact with the ground over here. So what I've done is I've placed a painter, and the painter here has a mass M, and the mass M of the painter here is denoted over here. And this painter is standing a certain distance from the edge or a certain distance from the wall. Okay, in this case, the total ladder here has a length L. And the painter is standing more than halfway up the ladder. I'm going to set him equal to 2/3 L. And this is kind of up to you. You could set it to whatever you want. In this particular case, I've picked this value. So again, he's painting the trim, so he wants to be almost all the way up the ladder. One other variable that I've denoted over here is the coefficient of static friction. This is a property of the material of the ladder that is in contact with the ground. In this case, I've set it to 0.4. Again, that'll depend on the two materials that are in contact with each other. One simplification that I've done here is that I will not include any friction up here. This ladder is also touching the wall, right? And depending on the two types of material, there certainly will be friction there. However, I'm not going to introduce that frictional force up here making contact with the wall. If you do include this, it's pretty straightforward. It will add another force to your free body diagram. In this case, I will not include it. Okay, so let me go ahead and just kind of explicitly say that for this case here, the coefficient of static friction is going to be 0, and that's between the wall plus the ladder. Again, if this ladder is of aluminum and maybe the wall is also aluminum, yeah, that might not be the best approximation, but I will do it in this problem nonetheless. All right, the next thing we want to do now is label all the forces acting on the ladder because we want our ladder to be in equilibrium. So this is what I've done here on the right-hand side. I've made a free body diagram on the ladder, which is outlined in orange, and here are all the forces acting on the ladder. First of all, we have a weight. And this is weight of the ladder. Notice that I've placed the weight right at the geometrical center of the ladder. And since the mass of the ladder here is lowercase m, the weight, which is the earth pulling on this ladder, is going to have a force equal to m times little g. All right, I've also included another weight over here. This is really the weight of the painter, right? The weight of the painter. Again, the ladder is supporting the painter, so he's also in equilibrium. But I can add the weight of the painter here as a force acting down on the ladder. Again, if his mass is uppercase M, and again, this is done on Earth, so the weight is simply m times little g, and we have this additional force acting down. The force up here, which I've denoted as the force N1, this is simply the wall pushing against the ladder. This is what I've called a normal force. And again, it's simply a force that's perpendicular to the wall because it's a normal force. And it's simply acting in this direction over here. I've included an additional normal force down here at the bottom, right? This ladder is resting on the ground and the ground is pushing up against the ladder. So I've denoted this one as N2. And then the final force and the critical one that I've included over here is the force of friction. And again, this ladder is not sliding, therefore it is a static friction that I'm looking at. And this friction force acts in this direction because it's trying to oppose motion. And the motion would be the sliding motion. And if it was sliding, this N would be moving to the left. But if I want to oppose that motion, I would put a force of friction that's acting toward the right like this. These are all the forces acting on the system. So now what we want to do is we want to apply Newton's laws, and really Newton's first law, because we want this ladder to remain in equilibrium. So let's go ahead now and set up our equations and see how we would solve for this. I'm going to keep the free body diagram over here. And again, I've denoted this distance here, which is where the painter was located. This was 2/3 of the total length of the ladder, and the total length of the ladder is just a lowercase l. All right, so let's now set up our equations. Again, we're applying Newton's first law, so what we want is the sum of the forces in each direction, right? In the x direction to be equal to 0. We want to add up all of the forces acting in the y direction, and those should be equal to 0. And then we also want to sum up all the torque acting on the ladder because we don't want it to rotate. Therefore, we all want those torques to sum to 0. So first thing we're going to do before we apply any of these laws, we're going to choose a coordinate system. And here, let me make the coordinate system in green here. For the forces, what I'm going to do is I'm just going to use a standard XY coordinate system like this. So positive X is to the right, positive Y is acting up. And for the torque, what I'm going to do is I'm going to assume that anything that makes the object rotate counterclockwise, I'm going to take that to be a positive value of the torque. And anything that makes it rotate clockwise, I'm going to assume that there is a negative torque. So let's start with equation 1, which is the sum of the forces in the x direction. Sum of the forces in the x direction. So let's see which forces are acting in the x direction. I really only have two forces in this diagram. There's this normal N1, and then there's the force of static friction down here, and they're acting in opposite directions. So therefore, this equation would look something like this. There's force of static friction, which is acting to the right. Therefore, I'm going to denote that one as positive force of friction. Let me just write it like this. And then minus this contact force, or the normal force from the wall acting on the ladder. And it's negative because it's acting to the left. And therefore, that there sums and has to be equal to 0. Next equation, sum of the forces acting in the vertical direction. So we have three forces in this case acting in the vertical direction. There are the two weights which are acting down, the weight of the man and the weight of the ladder. And then there's also this normal force here acting up. This one here should look like this, normal subscript 2, because it's a different one. It's not necessarily the same value. And again, then minus, I have the weight of the painter, uppercase M times little g, and minus the weight of the ladder, lowercase m times little g, and these here have to sum to 0. Now notice this equation over here. This is pretty simple. The second equation, I'm just going to rewrite. I'm going to bring all the weight on the other side, and I'm going to factor out a little g because I think I'm going to use this one in just a little bit. So I'm going to save a step here. This one here looks like this. I'm going to open up a bracket, m plus little m. So this is kind of like the total mass of the system, right? The guy plus the ladder, and multiplied by little g. Let me go ahead and box this equation. This one's pretty important. This gives us a value for this normal force. So if you know the mass of both objects, you can calculate what the normal force N2 is just by using this equation. All right, to calculate the torque, this is a little bit tricky for this problem. The first thing I'm going to do is I'm going to place a pivot point right here. And if I place it right here, that means that the torque due to the force N1, let me just write it like this, has to be equal to 0 because the distance to the pivot is equal to 0 for that case. And that means I'm left with calculating the torque due to these four forces. The formula I'm going to use to calculate the torque for any force is I'm going to say that the torque produced by any force F is going to be that perpendicular component to the force and multiplied by the distance from this force to the pivot. I'll just call it the distance d. This is the formula I'm going to use. Let me highlight that case, and then we're going to apply it to all of these different forces. All right, so the first one I'm going to consider is this weight, and the weight is acting straight down. However, I'm only interested in the perpendicular component of this weight. If you were going to draw that on this diagram, the perpendicular component of the weight should go in this direction over here. Maybe let's switch the color. Let me make it green. This is the component of the weight. If I've defined the angle theta as being this one, you should be able to convince yourself that this here is also the angle theta. And that would mean that this green vector should be written as mg cos theta. All right, I could do the similar argument for the weight of the ladder. Again, I can break that force down into two components. The perpendicular component of that force is this one. And again, this here is also the angle theta, if this is the angle theta down here at the ladder. And that means I have a similar expression for this perpendicular component of the weight. I'm going to do the same thing for the normal force and for the frictional force. I'm going to break both of those forces down into components, and it's only the perpendicular component that I'm interested in. All right, so let's go ahead and do that also. Here's the perpendicular component of the normal force. The normal force is acting straight up. However, the perpendicular component, again, this here also ends up being this angle theta here. So for this one, the perpendicular component of that force is n2 cos of the angle theta. The only one that's different actually is the force of friction. Here's the force of friction acting parallel to the ground. However, the perpendicular component of that force is this guy right here. And if that's the angle theta in here, the perpendicular component of the force of friction, let me go ahead and write it down over here. Let's write it as F friction and maybe just put a little perpendicular here. This would simply be the force of friction. Force of friction multiplied by sine of the angle theta. Okay, I'm now in a position to calculate the torque due to each one of these forces. So I'm going to go ahead now and sum up all of the torque acting on the system. Again, I've placed the pivot up here so I don't have to worry about the normal force N1. What I'm left with now is the torque produced by this component of the weight. It's the magnitude of the force, mg cos of the angle theta. Now the distance to the pivot for this force is this distance over here. And this is only 1/3 of L. Right? Because the painter is actually standing 2/3 from the bottom. That means he's 1/3 from the top. Now if I write this equation like this, I'm all done. Now I have to define whether this torque should be positive or negative. Again, if this is the only force acting on the system, it would tend to make the object rotate counterclockwise. And I've defined that counterclockwise as being positive, so let me just go ahead and do that. Plus, I'm going to have a term mg cos of the angle theta. That is the perpendicular component of the weight of the ladder. And now in this case, this force is acting right at the center of mass of the object, and that should be right at the center. That's L/2. Again, it's going to be positive because it would tend to make the object rotate counterclockwise. We can add now the torque due to the normal force. Now the normal force, again, that component is only n2 cos theta. And that one here, I'm going to write it as a negative value. Because if this is the only force acting on the system, it would tend to try to make it rotate in the clockwise direction. And I've defined that to be negative. So this here would be n2 cos of the angle theta. That's the magnitude of the perpendicular component of the force. Now the distance to the pivot for the normal n2 is the total length. It's the total length L of the ladder. All right, one more thing. Now I have the force of friction. Again, that one would tend to make the object rotate counterclockwise, so that one should be positive. I should have force of friction, sine of the angle theta. And the distance to the pivot is also the full length of the ladder, L. And that's it. That is the torque produced by the force of friction. And that there should be equal to 0. All right, that's kind of a lot of math. We have to digest this a little bit. So let's go to the next page and clean up all these equations and see how we solve for our angle. All right, so here are my equations. Newton's first law applied to this ladder. I've got some of the forces, some of the torques. And now what I want to do now is basically simplify this equation. However, I do want to note one thing. In the third equation here, I have two terms, and actually these are kind of linked together. The force of friction and the normal force are going to be linked together. And if you remember from your class, you should have seen in your class that at least the maximum force of static friction, so I'm going to write it as FF maximum. This case here has a very specific value. It's given by the coefficient of static friction and multiplied by the normal force, which in this case is the normal force N2. So actually what you can do now is kind of simplify this expression a little bit more, because we know what N2 is. N2 is simply the weight, the total weight of the system. So actually I can write this term as mu s and multiplied by the total weight, which is m plus little m, and divided by multiplied by little g. All right, now if I substitute the maximum force of static friction in my equation, that means whenever I have the maximum force down over here, that means that's going to allow my angle to be really the minimum angle that I'm going to have if this force here is maximum. So what I'm going to do now is just rewrite my equation. Let me move it over. I'm going to rewrite my third equation. However, I'm going to make some simplifications. So let's go ahead first and introduce the minimum angle that we're going to find. The minimum angle will be here. I'll just call it as min. I'll introduce a little subscript next to the theta, a little uppercase m for minimum. The other thing I can do now is substitute all of my force of friction down here. I could substitute that into this expression. And the other thing I could do is I can eliminate here the force N2, and N2 again I can simplify it, or I could substitute it with the total weight, which is m plus little m multiplied by little g. There is another simplification that happens. You notice that all the terms here have the length L of the ladder. Now the first two terms have also a term in the denominator, so I can't simplify that just yet, but I can certainly divide through by the total length. Since all the terms include the total length, it actually doesn't matter what the total length of the ladder is, which is kind of surprising. Now the reason you have a third here is because that was where the painter was standing, right? He was 1/3 from the top. And the reason you had 1/2 over here was because the weight of the ladder is acting at the center of mass, and I've taken that point to be at the midpoint of the ladder. So let's start with this expression over here. And actually the other thing I'm going to do now is I'm going to divide this entire equation, because at the end, really what I want to find is I want to find what this theta minimum is. But right now it includes combinations of cos and also of sine. And that's kind of difficult to deal with. However, if I divide through, I'm just going to write it over here, divide the entire equation by cos of this minimum angle, this is what it's going to look like. All right, the first term here looks like this. I'm going to have m over 3 plus little m over 2. Again, I'm dividing through by cos of theta m, so it'll eliminate this term. It'll eliminate this term. I still have a little g over here, so I can do that. What else? Minus, the next term over here is going to be this term, which is the torque due to N2. That ends up being simply the total weight of the system, multiplied by little g. Again, the cos is no longer there because I've divided through by cos of theta m. And this last term over here, again, includes this coefficient of friction. It's going to include the total weight, m plus m, multiplied by little g. And now I had sine theta, but I'm dividing through by cos theta. So at the end, what I end up getting is tangent of the angle theta, and that equals to 0. All right, if you look at this equation down over here, there is actually only one unknown in this equation. In this problem, I've told you that the coefficient of static friction here between the ladder and the ground was 0.4. So all we really have to do now is simply isolate and get an expression for tangent of the angle theta. So let's go ahead and do that now. All you have to do is bring all the other terms on the other side. Okay, if you bring all the other terms on the other side, this is what my final expression should look like. Tangent of theta m, which is my minimum angle, should be equal to something like this. Again, there's little g's everywhere. We can get rid of those. Little g, little g, little g. That simplifies the algebra a little bit. I'm going to bring this term on the other side. That becomes m plus m, the total mass. I have this term over here. That becomes a negative term if I bring it on the other side. M over 3 plus m over 2. And that's it for that term. And now I have to divide by, again, this whole term right here. It looks kind of messy, but it'll simplify in just a minute. This is m plus m, the total mass, and multiplied by this coefficient of static friction. All right, I'm going to look at this bottom expression here, and let's take some limiting cases to make sure that the physics works out. To simplify things a little bit, what I'm going to do now is I'm going to assume that the mass of the painter equals to the mass of the ladder. Now, you don't have to make this assumption, but I'm just going to make this expression kind of reduced to something that's a little bit more simple and easier to digest. And if you make that assumption, basically what you end up getting here is 2m for this term. This guy here becomes, this is still 5 over 6m. And the denominator becomes 2m. And multiplied by the coefficient of static friction. This becomes 12 over 6. That becomes 7 over 6. This looks like it becomes 7 over 12 multiplied by mu s. Okay. This is tangent of theta minimum. So for this angle here, actually, once you've made this assumption, the total masses actually end up canceling out, only in this kind of limit. What I end up getting if I solve for this expression is that theta minimum, let's just call it this. Using my calculator for this, I end up getting 55.6 degrees. Okay, so 55.6 degrees would be kind of the minimum where you could kind of safely stand at 2/3 if your mass was the same as the ladder. What you can do now is use this expression to calculate just about anything. I would also suggest kind of looking at this expression right here and just making sure that physically it kind of makes sense. What happens now if the coefficient of static friction is really, really small, right? What if it's almost 0? Let's just make it really, really less than 1, right? What happens in this limit? Well, in this limit, what would you expect? If there is no friction, you'd expect that you probably can't place that minimum angle, can't be probably has to be close to 90 degrees. So let's go ahead and take that limit. What happens? Again, if you're dividing through here by a very, very small number, basically this number here tends towards something very, very big. And the way you get tangent equal to something very, very big, you get that if theta minimum is approximately equal to 90 degrees, right? If theta minimum equals to 90 degrees, it means the ladder is basically straight up. How about if you take another limit? What if the coefficient of static friction was really, really big, right? If the coefficient of static friction was really, really big, you'd come up to this expression. You'd have tangent of theta min, and if I divide by a very big number, for example, this here would tend toward 0. And that means what? Well, that means that theta minimum in this case, tangent of theta equals to 0 means that the angle is basically 0 degrees. Yeah, if you have a lot of frictional force down here between the ladder and the ground, basically you can make this angle really, really small. So this is kind of like a sanity check. You know, do the results kind of make sense under the appropriate limits? And in this case, they do. For one specific example where we have a painter standing 2/3 of the way up and the mass is equal to the mass of the ladder, we get this value of the angle. Anyway, you can kind of hopefully understand how you could solve problems like this or similar problems to this one. Thanks for watching, folks. If you have any questions, leave them in the comments section. Remember to subscribe to my channel. Bye-bye.